or the last idea that we have covered last time, and that was the more efficient way of computing the fractional knapsack upper bound. Remember that for the fractional knapsack, for the branch and bound algorithm that we have studied for the 0-1 knapsack problem, we have covered 3 bounds. Upper bound 1, which is what? What's upper bound 1? Just count all undecided, take all undecided items. Upper bound 2, yeah, undecided items that fit. And upper bound 3 is the fractional knapsack. Now last time we said that the fractional knapsack can be computed incrementally at each node. So instead of computing, solving a fractional knapsack from scratch at each node, we start with one fractional knapsack solution at the root node, and then as we go down the tree, we just modify an existing solution. So if you have a fractional knapsack at a given node, you have a fractional knapsack solution. This fractional knapsack solution will have some items taken and some items undecided, and then there will be an item, in general, there will be an item that you have taken a fraction of. And this is what we call the, what did we call the item that we, the slack. Yeah, exactly. Yeah. So that's the slack item. So the slack item is the item that you have taken a fraction of. Now the idea is you have a given fractional knapsack solution at node X, and you move to node Y. Now in certain cases, the fractional knapsack solution at Y will be exactly the same as the fractional knapsack solution at X. And when will that be the case? When will the fractional knapsack at Y be the same as the fractional knapsack solution at X?
When the item is taken?
Yeah, when the item is taken. When you take, if it's take items, then you're going to get the same fractional knapsack at Y. And we have explained last time why. It's basically, it's just the same thing. You haven't changed anything. Maybe one item will change its status from undecided to taken. Okay, so the only difference would be that an item will change its status from undecided. It could be undecided here, and then here it will become taken because we have decided to take it if it was undecided. So it will basically, if there is a, in the fractional knapsack solution, the complete fractional knapsack, there is always that borderline between taken and undecided. And by taking an item, you are basically moving this line. So maybe we can draw something like this. So item 1, item 2, and then the rest of the items are undecided. And out of the undecided items, we decided to take items 3, 4, and part of 5. This is an example of a fractional solution. So when you take item 3, for example, when you decide to take item 3, now you will get the same solution, but the blue line will move down. So item 3, instead of being counted as an undecided item, now it's decided but taken. So you'll get 1, 2, 3. Now these are taken. So these are taken. These are undecided. So a fractional knapsack solution will have the taken items that you have already decided to take, plus the items that have not been decided yet, you will fit the maximum value out of undecided items, treating the problem as a fractional knapsack problem. Now, if you take item 3, what will happen is that the blue line will move down by one item, and these are the taken items now, and undecided items are going to start from 4, and this is part of 5. Now it's going to be the same, because now it's going to be the same solution, because now you are solving the problem. These are the remaining items, and the remaining capacity is going to change. So now if you had some remaining capacity here, CR here is going to be CR minus what? Weight of 3. The weight of item 3. So the remaining capacity here, if the remaining capacity is 10 and the weight of item 3 is 3, then the remaining capacity here is going to be 7, because we just subtract the weight of item 3. So if we take the item, it's not going to change anything. The only thing that will change is this borderline between taken and undecided. However, if we choose not to take an item, like we choose not take or untake item 3, so if we don't take 3, now the solution is going to be different, right? So now this will no longer be what we will have. What we will have is going to be this. Or let's draw it here. So you will have 1 is taken, 2 is taken, and now 3 that was undecided, now it's decided not taken. So now we have 4. So now the line is here, and now we can take something. We can take probably more of 5, and possibly part of 6, and maybe all of 6, and all of 7, and all of 8, depending on what?
Remaining capacity.
Okay, and what does the remaining capacity depend on here? What's the extra capacity? What's the extra capacity that we can use to fit more items here?
The weight of the item not taken.
Yeah, the weight of the item not taken. Exactly. So if we decided to skip item 3, then whatever the weight of item 3 is, so if the weight of item 3 is 3, then we have 3 more kilograms, and we can use these 3 more kilograms to fit more and to move down this list. So now this is our slack. Our slack is item 5. So we can move down the list. Now we could go to the next item or not, depending on these 3. So for example, if item 5, if the total weight of item 5 is 10, and at node X here, so let's put it here. So if the total weight of item 5 is 10, and we have already taken 9 out of 10, then with 3 more, we can take 1 more kilogram of item 5, and then we can take 2 kilograms of item 6. So here we can take all of 5 and part of 6. Or it could be, depending on the weight of item 3. So if we change the weight of item, if the weight of item 3 was a large value, like 10, for example, if the weight of item 3 was 10, then with these 10 kilograms, we can probably fit more. We can possibly take 5 and 6 and maybe 7, and then part of 8. Depending on the values of these items. So in this case, for assuming that here we took 9 out of 10, if the weight of item 6, for example, was 3, and the weight of item 7 was 4, then we have taken 1 more kilogram of 5, and 3 kilograms of 6, 4 kilograms of 7, so that's 8. Then we can take 2 kilograms of 8. Okay, so you use the additional capacity that became available after excluding item 3. You use it to fit more items. So you go further down the list. So it's a matter of going down the list. So in general, you can draw this in general at any node. You have a certain number of items, a certain item 1, 2, and this is your slack item. So in general, at any node, if you choose to skip item k, if you skip item k, if item k is the item not taken, then, sorry, this is the weight of k, and you are here, you will go down the list. You can possibly do s and s plus 1, s plus 2, all the way to s plus j in general. So generally speaking, you will move the pointer from s to another s plus j. Now j could be 0. S and s plus j could be the same item, and there are no items in between. And when will this happen? Under what condition will s and s plus j be the same? Under what condition precisely will s and s plus j be the same thing? No. Under what condition will s and sj be the same? S plus j be the same? It just means that, for example, giving some numbers here, let this be 5, and we have taken 3 out of 5, right? So we have taken 3 out of 5, and the weight of item 3 is 4, for example. If the weight of item 3 is 4, and at the previous node we have taken 3 out of 10, then all what you will do with the 4 extra kilograms, you take 4 more kilograms of s, and you stay in the same s. So you will not necessarily move to the next item. It depends on the weight of the current slack and the weight of the item that you have decided not to take. So if the weight of the item that you have decided not to take is not that large, it may only allow you to take a few more kilograms of the slack, if the slack is big enough, right? So if the weight of the item that you have decided not to take is less than or equal to the remaining weight of the slack item, then you will stay in the same item. You will not go to the next item, right? So it all depends on this weight and this weight. So in general, s and s plus j could be the same. Well, in some cases, s and s plus j could be the same. They could be different. And the items in between, there could be items in between, and there may not be any items in between. So it could be, for example, in this case, if you end up taking all of 5 and part of 6, if you take part of 6, then your new slack is going to be, okay, if you take 5 and part of 6, then what's the value of j here? What's the value of j? 1. J equals 1, because there is nothing in between. This is your s, and this is your s plus j, where j is 1. So if you only move to the next item, your j is 1. If you have 3 items in between, then your j is 4. Right? So if there are 3 items in between, like if you take 6 and 7 and 8 and then part of 9, Okay? Then this is s plus 1, this is s plus 2, s plus 3, s plus 4. So now j is 4. Okay? So this is, in general, the value of j can be anything between 0 and the difference between s and n. Right? Because s plus j cannot exceed n. There are only n items. Okay, now how do we prove? You know, I did this last time, but I don't think it was clear enough. The argument was clear enough. So how do we prove that by doing this, the time that we need from root to leaf, or the time from root to leaf, will not exceed O of n? Now, first of all, why would the computational time from root to leaf exceed n? So it's O of n, but in general it could be greater than n. Why would it be greater than n? And otherwise, why would an item be processed more than once? Or why would an item be processed at more than one node? Will that be possible? Will an item be possibly processed by more than one node?
No.
No? Well, here is an example, right? It's we took part of 5 at one node. Then at the next node, if the remaining weight, if the weight of the untaken item, the 4, is less than the remaining weight of part of item 5, we will stay in the same slack. So at 2 nodes, we're staying at the same item. We're not advancing. We will not necessarily advance to the next item. Because if the current item is big enough, we may stay at the same item for multiple nodes. Like if this item has a weight of 100, right? And all of these items that you may decide not to take have only a few kilograms, then you will get stuck at this item for a few nodes. So an item may get processed at multiple nodes if it's big enough. So to analyze, so this means that an item may be processed by more than one node, which means that the number of operations will exceed n. But last time, what we proved is that the number of operations applied to an item cannot exceed 3n. Why is that? Because when we count the operations, we will count slack operations and non-slack operations separately. So the idea here is, at any node, the number of slack item operations, or the number of slack items processed, is less than or equal to 2. Why is that? Why is the number of slack items processed at each node less than or equal to 2? Because by definition, a slack item is an item that you take a fraction of. So at any given node, this is the item that you start with. So the item that you start with is already a slack item. So you will process this item. But every item in between, the old slack and the new slack, is by definition not a slack item. Because every item in between, if there are any items in between, is not a slack. You will take all of it. Okay, so these S1 plus S2 plus S3, all of these items in between are by definition non-slack. Why? Because you will necessarily take all of them. So you can only take a fraction of the first and last items that you process at a given node. Only the first and last can be taken partially. Everything else in between, if any, if there is anything in between, must be taken completely. So this means that at any node, the number of slack items processed is going to be less than or equal to 2. But the number of non-slack items at one node is not necessarily bounded by a constant. Right? In general, the number of non-slack items that are processed at a given node is not bounded by a constant. And why is that? Under what condition will the number of items between the current slack and the new slack will be large? Under what condition?
You drop a relatively large item.
Exactly, yes. So the item that you decide not to take, the 3 here, is large. So this is 100 kilograms. And all of these items below the 5, you have a bunch of small items, like this is 3, this is 4, this is 5. A bunch of small items. Now, you drop 100. You drop this item with 100 kilograms. And if these items that are below the current slack have small weights, then you will take a whole bunch of them. Many, many items. So in this case, if this has a larger value, larger weight, then all of these non-slack items that you will be taking, this number can be large. It can be arbitrarily large. You cannot compute a bound on the number of items that on the number of non-slack items that you process at a single node. However, so this is bad news. This leads to O of n worst time at each node. Right? So this, what I have just said, that we cannot compute a bound on the number of non-slack items at each node, this leads to worst case O of n per node, which is not what we want. We're doing this whole thing to get something, to get an O of 1, not an O of n. So this is O of n per node, worst case. Now what's the good news? What are the good news? So these are the bad news. The bad news is that the number of operations at a given node can be in the worst case n, of order n. Now what are the good news? Now the good news is that when you process more items at the current node, then you are likely to process less items at the next nodes, because the number of items is limited. So the number of items cannot exceed n. We'll know that the number of items cannot exceed n. So by making progress at the current node and advancing the pointer through multiple items, like 10 items, these 10 items that you have processed, you're not going to process them at the next node, because the number of items is limited. Remember that we are counting the number of operations along a path from root to leaf. So an item, once we take an item completely, we will never go back to that item. Okay? Okay, now what does this mean? It means that even though we cannot set a bound on the number of operations done at a single node, we can set a bound on the number of operations that are done at all nodes, the aggregate. What the number of operations done at all nodes. Now, what's the bound on the number of non-slack items that are processed at all nodes? What's the limit? What's the bound on the number of non-slack items that we can process at all nodes? Well, by definition, by how many nodes can a non-slack item be processed? One node. By definition, a non-slack item is an item that you take completely at one node, which means that you will never touch it again in any of the next nodes. Right? So if all of these items in between, if you take them completely at the current node, you will never touch them again at the next nodes down the tree or along the same path. We're counting the operations, the sequence of operations along one path from root to leaf. So by definition, a slack item, a non-slack item can be touched by only one node. And there are only n items, which means that there can be at most n non-slack operations. Okay, so because a non-slack item can by definition be processed by only one node, the number of non-slack operations cannot exceed n. So now at any node, the number of slack operations or slack items processed is less than or equal to n. This implies total slack operations is less than or equal to what? Total slack operations is less than or equal to 2n, because there will be n nodes, right? So there are n items and n nodes, but we don't know how many items will get processed at each node. That's the point. So you know that you will have n nodes and n items, but you don't know how many items you can process at each node. So it could be that at this node, I'm going to touch 7 items. At this node, I will touch only 1 item. At this node, I will touch 2 items. At this node, I touch 10 items. Then I touch 1 item. So you don't know how they are distributed, how the items are distributed on the nodes. But definitely an item can be touched more than once. So the number of non-slack operations cannot exceed, the total slack operations is going to be less than or equal to 2n. Now total number of slack and non-slack operations is going to be less than or equal 3n, which means O of n. So the intuition behind this is that when you process a large number of items at one node, you are making progress down the list, right? This is the list of items, and you are going only in one direction. You never go back. So you are making progress down the list, which will save you more operations in the future. You will be touching less items in the future. Okay? So now this is O of n. Now, when you average this across the nodes, then on average, each node will get O of n divided by n, which is O of 1. So the amortized time per node is O of n divided by n, which is O of 1. Okay? So this is the argument that shows the O of 1 time. So the intuition behind it is that processing more items at one node will lead to processing fewer items at the nodes below it. Yes?
Why do we divide it by n? Because there's n nodes?
Yeah, because there are n nodes. So we're trying to calculate the average processing time per node.
So n nodes in one path?
In one path, yeah.
Oh, but not the whole tree?
No, not in the whole tree, definitely. Yeah, we're counting in one path. We're counting the operations in one path from root to leaf. And the path has n nodes in it. Okay, so now in the assignment, in assignment number 4, you will be implementing all of this. You will be implementing, and I have posted the assignment. You will be implementing brute force because we want to compare with it to see how slow it is. Although with in some cases it's not going to finish within reasonable time, but you can set a time limit of 1 hour in this assignment. If anything does not finish in 1 hour, then you count it as a timeout. So brute force, then you will do backtracking, then you will do branch and bound with upper bound 1 plus backtracking, branch and bound with upper bound 2 plus backtracking, branch and bound with upper bound 3 plus backtracking. Now what you are required to do is not the O of 1 implementation of upper bound 3. You can do the O of n implementation. The O of n implementation, you just write a fractional knapsack routine and you invoke it at each node. Okay, so that will be easier to implement. You just start over at each node. At each node, start over, you compute, you call the fractional knapsack routine, and what do you pass to it? Which items and which capacity. So in order to call, when you call the fractional knapsack, you have to pass to it certain items and certain capacity. What do you pass to it at each node?
The items and the remaining capacity.
Exactly. You pass to it the remaining items and the remaining capacity at each node. So that's going to be the O of n. Now, if you do this, you will satisfy the requirements. But you will get extra credit if you implement the O of 1, the incremental algorithm that I have just described. And this should make a big difference in terms of solution time. Okay, so in this assignment, there will be 30 points of extra credit. And the student who will come up with the fastest branch and bound algorithm will get the 30 extra points. Okay, so the fastest program will get the extra 30 points. If you are the second fastest or the third fastest, then you will get a good part of this. You will get 10 points if you just do the O of 1 fractional knapsack implementation. So you get 10 out of 30. You are guaranteed to get 10 extra points if you do the O of 1 fractional knapsack that I have just described. So you will get to see this incremental calculation of the fractional knapsack, how much difference it will make. Okay. Okay. Any questions on this?
So how does this affect the overall complexity of the algorithm?
Oh, that's a good question. How does this affect the overall complexity of the algorithm? Well, in the worst case, in fact, we are not making any improvement. So this is an interesting question because from a theoretical point of view, from an asymptotic complexity point of view, the algorithm is still the same. It's still exponential because in the worst case, you're going to visit an exponential number of nodes. But in practice, it's going to make a huge difference. So the difference in practice is going to be like reducing the solution time from billions of years to seconds. Okay, so this is something where there is a difference between theory and practice. In theory, this is not an improvement. This is still a worst case exponential algorithm. But in practice, you can solve some instances like size 100. We did the calculations in the early lectures. With 100 to power 100, that's billions of years. But if you implement this, you can solve 100 in seconds. Okay, but the worst case asymptotic complexity is still the same. So from a theoretical point of view, this is not an improvement. It's a practical improvement. From a practical point of view, it makes a huge difference. From a theoretical point of view, it does not make a difference. Okay. Any questions? So this, this assignment should be a very good learning experience, and it's open-ended. So we don't know, how fast the fastest implementation is going to be. You can come up with your own ideas and with your own implementation tricks. You can even implement ideas from published work as long as you cite them properly. If you take ideas from any publication, you just cite it, and you will get credit for the implementation. Okay? In fact, I posted a paper, published research, where they publish their results, and they can do, let's see, I think they can do 100 items in 2 seconds, and they can do 500 items in 13 seconds. So they report solving 500 items in 13 seconds. Yeah, so let's see how close you can get to that. If you can solve hundreds within seconds, that would be a great accomplishment.
But
yeah.
for the real-world application of this, you still have to have a pretty small n, right? I mean, because that's not going to scale.
Well, what are the applications? It depends on the applications, right? So it's, and we are not particularly interested in the 0-1 knapsack. We are interested in any problem that is difficult, that is hard enough to require, branch and bound. So there are interesting problems, interesting hard problems that require branch and bound, and the input size is hundreds or even thousands. Okay, so in my research, I do scheduling problems, and we do hundreds, and some of the instances are thousands of. They have size in the thousands range. Okay. Yeah. So don't assume that the input size is always small. In fact, if all the input sizes were small, then we wouldn't have needed to learn algorithms. The whole science of algorithms would be unnecessary if all input sizes were small enough.